Good morning. Welcome to Krishna's class. This talk we focus on exploring when equality occurs in Holder and Minkowski inequalities. In fact, you recall in our last two lectures, we have essentially proved these two inequalities. And they were very short lectures, and we have not considered the situation when equality occurs in this case, because this is relevant for our discussion on LP spaces. Now let me just quickly recall the main steps of the proof of these two inequalities, so that we are able to explore the equality scenario. Okay, so we start with we outline the proof of Holder's inequality. I need some of these notations to explain what is the result. That's why I am doing it. So P and Q are conjugate exponents. That is 1 by P plus equal to 1. Both P and Q are real. So real, positive. So we have the situation that is we are assuming 1 less than P less than infinity, 1 less than Q less than. Now let us use the following notation. Let A designate integral over x B designate g to the power q Now we first dispense with the situation where either A or B is equal to 0. Okay. If A equal to 0, this means this integral vanishes. Then f is equal to 0 almost everywhere, which implies fg equal to 0 almost everywhere on x. Okay, and consequently, you see that if you take up this, the left hand side of the integral becomes 0, is less than or equal to 0, and that proves 1. Now, if A is positive and B equal to infinity, then one holds trivially. Okay. So we shall assume that hence we shall assume that means f is an LP function and g is an LQ function. Okay, so that is the assumption that we are making. But this integral is finite and this integral is finite and they are non-negative functions that you are taking, and you are assuming that they are not equal to 0, because the case where a equal to 0 or b equal to 0, to get this automatically this inequality 1. So this is the assumption that we are making. Okay, so we have this finite also finite. So these are the assumptions or implications by our assumption. Now this implies, so we take this as 3, and this in turn implies integral, okay. So we will take, define capital F and capital. So we define F to be okay. We shall put if we take out the statement of the theorem, shall put capital F as F by A and so denote this by okay. Now this implies integral over A x F P d mu equal to integral over x G Q equal to 1. That is very simple. So we designate it like so if x is such that and if then there exists real numbers real numbers s and t such that for that x fx equal to e to the power s by p and equal to remember we have assumed that the functions f, small f and g have range the set 0 to infinity included and 0 included. Okay, therefore these are non-negative. Okay, right. Now equal to 1, that means p and q are conjugate exponents. By the convexity of the exponential function, by the convexity of the exponential function, we have the following inequality. And that is at the crux of proving this theorem. We have the following e to the power s by p plus p by q is less than or equal to 1 by p e to the power s plus now this comes from this. See that if you have a function psi which is convex, then psi of where alpha and beta are taken to be 1 by p plus 1 by q, and this is less than or equal to so we are just using that. So this is actually psi of s by p plus p by q, where alpha is taken as 1 by p and beta is taken as 1 by q, and then you have this inequality. Okay, so I just recall that at that stage, and that is straight away true. That is from the convexity. In fact, it just means the following. Okay, suppose this is t. Suppose this point is 1 by p, yes, so that it is some intermediate point. And you know that this function is a function which is convex. And what is the meaning of that? See, this is the exponential function that you have, and you see take this line joining these 2 points. So this is e to the power, this is e to the power t. And then you have by linearity, this point is e to the power 1 by p s plus 1 by q t. So this height. Okay, so this point is actually s. The coordinates of this point are, and the coordinates of this point are this is the point. And you see that this point has coordinates 1 by p s plus 1 by q t, and the height is e to the power Therefore, you can easily see with the statement that you are making is this particular height is greater than or equal to this particular height. Okay, that's the statement that I am making. That is e to the power 1 by p s plus 1 by q t is less than or equal to 1 by p sorry, I think I should write here. This is 1 by p so e to the power 1 by ps, sorry, 1 by e to the power 1 by ps plus 1 by qt is less than or equal to 1 by p e to the power s plus 1 by q e to the power t. Now this is the statement that you are making from the convexity. Okay, what is the consequence? That is, you take fx into gx. Now this is less than or equal to, you can substitute for e to the power s by e. So you will get 1 by p gx to the power q. Okay, so this is the statement that you make, and this inequality you can designate by and this is what you have. Now this is true for almost everyone, okay, for almost all x. So you have this inequality. 6 is valid. Almost every. Now we shall just integrate to obtain equal to 1. Now, this inequality, this comes from the fact that integral over x f d mu, that is by 4. Okay, so that now this is we shall also outline the Minkowski inequality, the proof of Minkowski inequality, and then together, we shall consider the equality problem in both these cases together. So we will next write down what is Minkowski. So we shall write f plus g to the power p is equal to f into f plus g to p minus 1 plus g times you might wonder why we have assumed that both f and g are non-negative. Okay, but that is no restriction at all, because in the case of LP spaces we will be talking about LP functions where the integrand that appear will be integral over x mod f to the power p, which is again a measurable non-negative function. Okay, so it will come to this. So this is no restriction at all. Okay, we are just assuming to avoid writing all sorts of absoluteness and so on in our. Okay, so denote this by 8. Now, what we do is, to each of these terms, we will apply Holder's inequality. And we get two inequalities, which are, understanding that is essentially important in getting the equality. So what we have is the following. We will write the following inequalities. Inequality, we have integral over x f into is less than or equal to one by q. And similarly, this we call and we have another inequality with g 1 by p, and this we designate by 9. Now note that p minus 1 times q equal to p, because we have 1 by p plus 1 by equal to 1, which in turn means p plus q equal to pq. That's the condition. Okay, so this is true, and consequently we have, let's write down this integral over x p minus 1 q equal to p, therefore this is p into one by p. And now you have to show that if this is not equal to 0, then you can immediately cancel that, the corresponding factor from what is there on the left hand side, and you will get the result. Okay, so denote this by that. So sufficient to prove Minkowski inequality 2 when the LHS is the left hand side is greater than 0 and the RHS is less than 0. Because less than infinity. Because in those two cases it is obvious that it is true. Okay, so we use once again convexity to prove that. See, the problem is that you will have to show this is not equal to 0. Then only you can divide by that. Okay, by p to the power p for infinity, we have again we are just using convexity. This inequality is valid, and hence you see by our assumption that, and hence by 3, that is the assumption that we have made, the less than infinity. The reason is if you just integrate this over x, integrate over this, integrate this over x, we have integral over, and this is this one is what we have assumed as a, and this is and we are assuming that this is an LP function. Okay, so here we are assuming infinity. So these two conditions. Okay. Therefore, I just now you can divide by one by q and use equal to 1. Minkowski inequality. This much we have stated or proved earlier, but I just recall this because we need some of these numbers to explain what goes on. Now we are in a position to take up the equality problem. So let us take up that. Hold this. So the question is, when does equality hold in the Holder's inequality? Well, that means we want to, if possible, a characterization theorem. Okay, so we are looking for that. Is it possible to characterize it? That's the question that we are asking. Okay. So we just work backward from some of the inequalities that we have used. Equality holds if and only if is equal to 1 by p plus equal to 1. That means you are using equality here. This is 7 with equality. So that is equivalent to equality in 6. That is, we have fx equal to 1 by p and we know that in 5 equality holds if and only if s equal to. What does that mean? It means you are taking the convex function e to the power s or e to the power s and t. Now you see that you know it's a convex function. So the exponential function is a convex function. It's a convex function. And you see that this is s, this is t, and this is somewhere here half s plus half t, or 1 by p s plus 1 by q t. Is in between. Now you see that if s is strictly less than t, then you see that you don't have equality in that relation. Okay, you have equality. See, the problem is this. This is exponential at this point is this height, and this is less than the 1 by s plus 1 by t. 1 by p s plus 1 by q t. Okay, but when are these two equal? These heights are equal. These heights are equal only when S and T coincide, and that's a statement that we are making. Okay, and what is the meaning of that? That is, if and only if almost everywhere. And what does this mean? That is, if f to the power p by a to the power p equal to g to the power q divided by e to the power. Okay, and that is if and only there exists positive constants See, these two are, one is a scalar multiple, a positive scalar multiple of the other. There exists constants positive. Alpha, beta, not both 0, not both 0, such that alpha times beta times so that is the condition for this. So f to the power p and g to the power q are linearly dependent with positive constants or through a relation of this kind. Okay, so this is the criteria for equality in X. Now we shall use this to explore equality in Minkowski. That's our next task. The Minkowski inequalities, that is equal to one by when does this happen? See, it is quite easy to see what goes on. If F and G are linearly dependent. That means suppose G is a alpha F. Then you have integral over x this is equal to integral over x integral over x f into 1 plus alpha by p then you can write this as alpha to the power p okay which is equal to see this alpha is a constant equal to into integral over x by 2. Therefore, hence the right hand side is actually 1 plus alpha integral now consider this one. Now this is equal to 1 plus alpha to the power p 1 by p. So this is 1 plus alpha therefore these two are equal. Okay, so if f is a scalar multiple of g or there is a linear dependence with a positive constant, something like alpha f equal to beta g, where both alpha and beta are positive, then this inequality holds, and that's quite easy to. Okay, but we want to prove that this is if and only if. So one way it is easy. Okay, so we explore whether this condition is also a sufficient. I mean, it's a sufficient condition, but is it also a necessary condition? It's a sufficient condition. We have seen that if G is equal to alpha f, then the Minkowski inequality. necessary condition. For that, what we do, we observe the following. That is integral over x one by b if and only if equality and okay. So what are the statements that we have in 9a and 9b? These are integral f into equal to integral over one by q, and so also you have the second inequality one by q. Okay, so this is, see, these are application of on this part of the Holder's inequality, and you know precisely when Holder's inequality you have equality holding, that is we have fg to the power, there exists non-negative constants alpha and beta such that f plus g to the power p minus 1 equal to alpha times f, and f plus g equal to beta times g. What does this mean? These two are equal to alpha times f plus beta times g. Suppose it is not true, then one of them is going to be a strict inequality. A strict inequality means that you are going to have strict inequality, because this is the crucial inequality that we are going to apply in obtaining this inequality. Just analyze the proof of the Minkowski inequality. Okay, this with inequality we are going to apply. So if equality prevails here, then only this will, you will get equality here. If equality does not prevail in one of them at least, then you see that inequality is going to prevail here. Therefore, in both these 9a and 9b, equality should hold, and now you use the criteria for that, from the Holder's inequality. Okay, so when when do you have equality in the holders inequality? So we use that. So that is given by these two. And this implies there exists alpha positive such that alpha f equal to the h. So that is the proof of this theorem, and that completes the proof of the statement of holders and Minkowski inequalities. Thank you very much. Let me wind up this talk here. Okay. Now we have set the stage for defining the normed linear space LP. Okay, right? So we have now all the tools required for this. We will explore that. Okay, thank you very much.